topic on hyperspace.
Okay.
I'm thoroughly interested in string theory again, but I know that hyperspace.
I think I read that one.
Okay.
Okay.
So, now, next topic, which is another one we spent a good bit of time in intro physics, well, physics 111, talking about. So it is review, but it's really important, so we're going to talk about it in quite a bit of detail. It is called, historically, the first law of thermodynamics. It is conceptually really nothing more than a statement of conservation of energy. So in other words, in a very, very broad sense, all this law says is, you have a system. It's surrounded by its environment. If it gains or loses energy to or from the environment, that will show up in its own total energy. So whatever energy goes into the system from the environment, that's going to make the total energy of the system go up. Or whatever energy comes out of the system and going into the environment, that's going to make the total energy of the system go down. And you can't lose any energy. That's all it says. And then we just have to apply it correctly and all be agreeing to what the various terms mean. Okay? So here come the terms that we're going to use. First, the concept called heat energy. What do we mean in physics by that? Well, heat energy is that energy which flows spontaneously, you don't have to force it, from one object to another because of a temperature difference between the objects. Okay? You put two objects in thermal contact. If they have different temperatures, they will exchange energy spontaneously, meaning you don't have to force it. Okay? And that energy which is transferred between them because of a temperature difference, we call heat energy. Symbol for heat energy, capital letter Q. Since it's energy, the SI unit must be joule. Then there's work, which you certainly remember from mechanics. Okay? But for us in this class, we're going to define work as any other transfer of energy between two objects, i.e. any energy transfer that is not due to a temperature difference and is not spontaneous. You have to force this one. Okay? And the symbol for that energy transfer is a capital W. But it is an amount of energy, so the SI unit had better be joule. Okay? It's very important to understand that both of these quantities, heat energy and work, are forms of energy, what I describe as being in transit or being transferred from one object to another. It's energy being transferred from one object to another. So for neither of these quantities, neither heat nor work, can you or should you talk about a single object as having a certain amount of them. You don't take a single system and ask, how much heat does it have? Understand what I'm saying? That question has no meaning. Right? Or to say something like, oh, that system has 10 joules of heat. That is an incorrect physics statement. Heat is not an energy that a single system contains. It is the energy that is transferred between one system and another because of a temperature difference. Same thing is true for work. You cannot point at a single system and say, oh, this system has 5 joules of work. That probably does sound odd to you. It should sound odd to you because it's wrong. Okay? You can't talk about a single system containing a certain amount of work. Work is energy that is transferred between one system and another, usually by means of a force. Okay? So don't talk about a single system having heat. And that one is the tricky phrase because a lot of people want to say that. oh, the system has 10 joules of heat. You've got to avoid that because it actually has no meaning to say that. You can talk about, oh, this system transferred 10 joules of energy as heat between itself and its surroundings. That's okay, that's correct. So watch out for that, especially with heat. Okay? And of course the reason that we fall into that trap with the idea of heat is because historically we used to think that a system did contain heat. Okay? They used to think of it as a kind of a fluid that the system contained. Right? That's no longer correct. Let me also tell you a little bit more about symbols, at least what I'm going to use. For work, I'm going to use the symbol W with a subscript on. And we're going to talk about the work done on a system by its surroundings. That's what the symbol for work is going to mean. It's going to be the work done on a system by its surroundings. So if we consider our standard dilute gas in the box that I talked about before, the way you would have work done on the system by the surroundings is you allow that piston to move. And then maybe you contrive to have an applied force on one side here of this piston pushing down. We will say that if the gas is being compressed, that the work done on the gas is positive. If it's being compressed, the work done on it is a positive number. We could, however, contrive, by changing how much this applied force is, to have the piston move up. Then the gas would be, inside there, would be expanding. That could happen. But then we'll say that if the gas is expanding, the work done on it is a negative number. So watch out, W means the work done on the system by its surroundings. W is work on is positive if this gas is being compressed, and it's negative if the gas is expanding. And you can have other things besides the gas in the box, but that's what we're going to talk about mostly in this chapter. Alright, so you've got heat energy and work, both as energy being transferred between a system and its surroundings. Here comes another idea. The total energy of a system. That's going to be important. Just what is its total energy? Here's the symbol. In thermodynamics, the symbol for total energy of a system is a capital U. Now, you may not be used to that. You might have thought we're going to use E. Well, that's not what most textbooks use. In the field of thermodynamics, the total energy of a system, the symbol used is capital U. And I know that might be confusing. You might prefer E. You might be used to using capital U for a very specific form of energy called potential energy, which is how we use it in mechanics. But in thermodynamics, the symbol U just means the total energy of the system. Okay? Now, it'll often be the case, it certainly will be true in this chapter, that in thermal physics, we don't consider systems where the center of mass of the system is being accelerated. Okay? That would be like if I took this box and, say, threw it across the room. That would be accelerating. The center of mass is somewhere right about in here, right? If I just took the whole box and threw it across the room, that would certainly mean its center of mass of that system was accelerating. We don't tend to do much with that. Mechanics is the field of physics where you study systems that are being accelerated. We don't tend to worry too much about that in thermodynamics. Nor do you tend to do many experiments in the lab where your whole apparatus is being accelerated across the room. Okay? So we're not going to be very interested in thermal physics in situations where the center of mass of the whole big thing is being accelerated, moved around the room in any kind of complicated way. In that case, the total energy U of the system really is coming from what we call internal degrees of freedom, things that are going on inside here, not from the thing as a whole being moved across the room. Okay? And when the total energy is coming from internal degrees of freedom, things that are happening inside, we tend to call that total energy the internal energy of the system. Okay? So as far as we're concerned in this chapter, total energy of a system and internal energy of the system are the same. So what would be contributing to the internal energy if my system is the gas in the box? Well, certainly I've got all the atoms and or molecules zipping around inside, so they have some kinetic energy. That's contributing to the internal energy, U. They interact with each other, perhaps only occasionally, but they do. There's probably a potential energy function that describes that. So that has to go into the internal energy. Einstein, E equals mc squared. Just because they have mass, they have energy. That goes in there. If the whole thing is immersed in an external magnetic field from a big magnet, and the atoms have a magnetic dipole moment, that's going to give you energy. You just have to add up all the things that are going on. Okay? Inside, though. It's just from what's going on inside. See, that's why it's called internal energy. So that's what we'll call it, most likely. We'll call it internal energy. So here comes the first law of thermodynamics. And again, it's just a statement that energy isn't lost. Okay? So here's what it says. As far as we're concerned in this class, there are two ways the internal energy of a system can change. Notice, change in capital U for a system. There can be energy transferred in or out as heat. That's this term. And there can be energy transferred in or out as work. That's this term. And the total energy transferred in or out from these two mechanisms will show up as the change in the internal energy. So in a very simple sense, if I've got a system and it gains 5 joules of energy through heat, and it loses 2 joules of energy by work, then the change in its internal energy will be 3 joules. I mean, that's pretty simple. And that's really all it's saying. Okay? Now we have to be careful though, that since it's a conservation of energy idea, plus signs and minus signs are important. So we have to all agree on when do we give things plus signs and when do we give them minus signs. We've already talked about W and when it's positive versus negative. If the system, it doesn't even have to be the gas in the box. If the system is being compressed, W is positive. If the system is expanding, W is negative. Here's the rule for Q, energy transferred as heat. If the energy is coming into the system as heat, Q is positive. If the energy is going out of the system as heat, Q is negative. We've got to stick to that convention, or we're going to get all confused. Okay? Just one more warning about notation. Your author, instead of writing W on, just uses the symbol W for work. But I like to add that subscript to remind you that I'm talking about the work done on the system by its surroundings. Okay? Another warning. If you do go back to your intro book, like Fundamentals of Physics, to review thermodynamics, chapters 18 and 19, you will discover a different notational convention. There, the symbol W will mean the work done by the system on its surroundings. Just a kind of the inverse of what we mean here. There, all you got to remember is that the work done on a system by its surroundings and the work done by a system on its surroundings are just negatives of each other. So if you look in the intro book, you'll see the first law of thermodynamics as delta U equals Q minus W. Because the W they mean is not the work done on the system, but the work done by the system. And W on and W by are just negative signs. That's the only way they differ. Now, when I teach 111, the notation I use whenever I write it on the board is I write it W by. And here I'm writing it as W on. Okay? All right, we're going to do lots of applications of that. We're going to do problems and so forth. Okay? All right, here's another important point. The concept of a function of state in thermal physics. I don't want to get too deep on it, and you don't need to get too deep on it. A function of state is exactly what those words mean. It's a quantity that depends only on the state of the system at a given time, and not on what happened in the past. How did we get to this particular state? We don't care how we got there. It's just what's happening now. Okay? So a function of state for a system in equilibrium, remember equilibrium means nothing is changing with time, is any physical property, a function of state will be any physical property of the state that has a well-defined value, like temperature, pressure, energy, volume, okay, at a given moment, based on the state it's in. The key thing to note is the things that do not go into the category function of state. And there are two, heat and work. Because that would be to imply that the thing has some amount of heat or some amount of work when it's in a given state. And that's not what heat and work are. So whereas these things listed here are functions of state, the most important probably being energy, internal energy, all forms of energy, heat and work are not functions of state. So, for example, let's say a system undergoes some kind of experimental process in the lab. Imagine the gas inside the box apparatus. And we're going to have it undergo a process. A process means an experiment. Okay? And in this process, or this experiment, we're going to go from one equilibrium state to another. In most of the experiments we're going to do this slowly and carefully and in a controlled way. Okay? All the functions of state of that system will depend only on where you started and where you ended, and will not depend on what happened in between. So the internal energy, for example, if you want to know how much it changed as you went from the starting equilibrium state to the ending equilibrium state, just take the value of the internal energy at the ending equilibrium state minus the value of the internal energy at the beginning equilibrium state. Okay? So the change in internal energy depends only on the energy in state 1 and the energy in state 2, and doesn't depend in any way on how you went from 1 to 2 in your experiment. Okay? It does not matter how you went from state 1 to state 2 in your experiment. Delta U doesn't care. Okay? But the quantities like heat and work, because in going from state 1 to state 2 in your experiment, you may very well have allowed your system to exchange energy as heat and work with its surroundings as you did the experiment. The values for Q and W, they do depend on exactly the details of the experiment as you go from 1 to 2. Okay? Because Q and W are not functions of state. So let me give you some more specific example of how we're going to apply this. Okay? I'm going to show you our first example of a PV diagram for this class. That's a plot of pressure of the system on one axis versus volume on the other. Okay? And we're going to imagine a couple of different experiments with our kind of standard dilute gas in the box. Okay? And we're going to have this gas go from equilibrium state 1 to equilibrium state 2 with two different processes, two different experiments. Okay? So let's look at these states on the PV diagram. I've scaled the two axes so that they're dimensionless. This vertical axis is pressure divided by the initial pressure, and the horizontal axis is the volume divided by the initial volume. Okay? So state 1 is at the point 1, 1 on this diagram, because the pressure is at its initial value and the volume is at its initial value. So state 1 of this gas in the box had some initial pressure and some initial volume, right? And we're starting at this point right here on the PV diagram. Where are we going to end up after the experiment is over? That's going to be state 2. We're going to end up right here. And in state 2, the final pressure will be 2/10 of the initial pressure, based on this graph, and the final volume will be 5 times the initial volume. So clearly this gas is going to be expanding to 5 times its initial volume, and its pressure is going to be going down. And I'm going to get from state 1 to state 2 using two different experiments, which I want to describe. And I want to make sure it's clear how you're going to do these experiments if you actually had the apparatus in front of you. Okay? Because it's a clever little apparatus, and it's quite well designed, at least from a teaching perspective, because you can control everything with it. So here's the container. Don't worry about that valve I talked about earlier that would let particles in or out. No particles are going in or coming out. Okay? Then here's the piston. Remember, you can put the locking pin in if you want to keep the piston so that it does not move. But if you want the piston to move, you've got to take that locking pin away. Then down here is a thermally conducting base. So I can let energy go in or go out as heat through the base. And by letting the piston move up or down, I'm in essence letting energy go in or out in the form of, what's the other transfer energy? But what's the energy form? Yes? Work. Right? I can let energy go in or out via heat through the thermally conducting base, or I can let energy go in or out by letting the piston move, volume change. That's work. Okay? Alright, so let's do experiment 1. The PV diagram is a curve that connects from point 1 to point 2. It's right here in blue. That's experiment 1. It happens to be described by a fancy word there that you see. What do you think that word means? Talk about that.
Temperature remains constant.
Temperature remains constant. ISO, constant. Thermal, in this case, means temperature. This experiment is done at constant temperature. Presumably, I can contrive to have a thermometer in here somehow. Right? So I can measure the temperature of the gas.
You can usually do that by compressing pretty slowly, right?
Everything's going to be done slowly. Yes. Okay? Everything's going to be done in this diagram slowly. So how could I possibly do experiment 1? I've got to bring the pressure down. Yes? Volume goes up. Temperature doesn't change. So the first thing is, and this one is the one that takes a while to get used to, there's got to be a way to control the pressure of the gas. Okay? Anybody know how the pressure is controlled? It's a bit subtle. It depends on, it could be the heat. It depends critically on whether or not that locking pin's in place. Okay? Clearly in process 1, you tell me, do I have the locking pin in place or not? No, otherwise I can't get the volume increase, right? So the locking pin is gone. When the locking pin is gone, there is one thing only that determines the pressure of the gas. I'm telling you, it's subtle. Here's a hint. There's no friction between the piston and the wall of the container. So, if there were any pressure differential between whatever is on top of the piston and the gas, the piston will adjust to equilibrium. Alright? Even the tiniest pressure difference, the piston will adjust. So the pressure of the gas will always be the same as the pressure of whatever is on top. So if I want to control the pressure of the gas, all I've got to do is control the pressure from whatever is on top. See what I'm saying? Now the way you would do that is you have a whole bunch of little masses, as small as you want. And you can control how many you put there. You can put more on if you want to. You can take some off. Okay? You thereby control the total weight on top. See what I'm saying? And by controlling the total weight on top, you're setting the pressure on top. And therefore you're setting the pressure on the bottom, which is the pressure of the gas. Okay? So, how do I get the pressure to go down?
Remove weights.
Take weights away. That's how you're controlling the pressure. Okay? But I still want the piston to move which way? Right? Volume's got to go up, yes? So what other things do I have at my disposal? Because you might be inclined to think, well, if all you do is take these away, what's the piston going to do? It'll go down. I don't want that to happen. So how do I make sure the piston goes up while I take weights away? There's one other thing I have at my disposal. What's happening down here? there's energy transfer via heat. Presumably I have like a hot plate or something down here, yes? Okay? That's what's happening on the other side of my thermally conducting base. So I will slowly adjust my hot plate. Now if I want that piston to go up, what am I going to have to do? I'm going to have to turn the hot plate up to make that thing go up. Okay? But I've got to do all this very slowly, and I've got to keep an eagle eye on that thermometer, because I've got to make all these adjustments so that the temperature never changes. I'm not saying it's an easy experiment. It's not too hard to talk about to do. It would be hard to actually do. It would take a lot of practice. But it, in principle, could be done. Okay? Very slowly, yes.
So you never account for adiabatic processes?
Well, that would be different. That would be a different experiment. You can definitely do adiabatic processes. We're going to spend a lot of time talking about adiabatic processes. This is not an adiabatic process. For those of you that don't remember what adiabatic is, don't worry right now. We'll talk about it. Okay? But watch out. Isothermal is the word for this process. And I will just say, isothermal and adiabatic are not the same. Okay? All right. So in experiment 1, we reduce the pressure and we increase the volume in just the right proportions so that the temperature of the gas never changes. And we stop when we end up at 2/10 of the initial pressure and 5 times the initial volume. And experiment 1 is done.
I don't understand why taking weights off would make the piston go down.
Well, if you didn't add any other energy, you just might be inclined to think, oh, I take a little bit away, it's going to sink down a little bit more because I've made the pressure less on top, but I haven't done anything to the gas. See what I'm saying? Okay? And if I didn't do anything down here, and you start to take these away, it's going to start compressing down. But I'm going to add energy down here too. Okay? I have these 2 parts at my disposal. Okay? All right. Point is, we'll learn a little bit later how you would end up actually calculating the change in internal energy for this experiment. Because there's some internal energy at the end, U2, some internal energy at the beginning, U1, and there's a change, delta U, for this experiment. Okay? I don't want the details now about what that number would be for this experiment. Just the fact that you could, we know enough, there will be enough physics we will learn to figure that out. Now we're going to reset the gas to the same state 1. And we're going to end up at this final state 2 again, but we're going to do a different experiment, a different process. And that's represented by the 2 red lines in the PV diagram, which is kind of 2 distinct parts to it in this second experiment. This part, the vertical red line, followed by this part, the horizontal red line, where I still end up at state 2. Okay? So let's talk about how we would do the experiment of the gas in the box for process 2. First step number 1. I need to bring the pressure down to 2/10 of its initial value, going vertically on the PV diagram. So that clearly tells me that the volume can't change. Right? So how do you think I would do that with this apparatus?
Lock the piston and
Yep, lock it.
increase the heat.
And you don't have anything left at your disposal but the thermally conducting base, but you want the pressure to go down, right? So turn the hot plate down slowly. Okay? And you could also have a pressure gauge in there. Okay? Because the weights up here do nothing for the pressure if the locking pin's in place. That's important to understand. If the locking pin's in place, how many weights are sitting up there has nothing to do with the pressure. Okay? Because the locking pin keeps the piston moving fixed, no matter how many things you put on top. Very important to know whether the locking pin's in place or not. Okay? All right, so the only way I have to control the pressure if the locking pin is in place and fixing the volume is through that base, the thermally conducting base. So I will turn that slowly down until my pressure gauge tells me that I'm at 2/10 of my initial pressure. That's phase or step 1. Then I have to do this process along here, this part of the experiment, where I increase the volume to 5 times the initial value. Notice what that means about the pressure for this part. It's constant. Okay? So how do you think I'm going to do that with the apparatus?
Slowly heat it while you remove weights.
Well, first of all, what am I going to have to do with the locking pin? Got to go away if I'm going to change the volume. Okay? Now I want the volume to go up while the pressure is constant. With the locking pins gone, what determines the pressure of the gas? The weights. What do I want to be true, have true about the pressure of the gas in this part of the experiment? It's constant. So what do I do to the weights up here? I don't do anything with them. I keep them fixed.
Then you heat it up slowly.
But I still want the volume to go up. So the only thing I have at my disposal is to go through here again. Right? Add some energy as heat, slowly, until the volume ends up 5 times what I started with. Then I will be at this point, where I was at the end of experiment 1. Right? So notice in experiment 2, I started and I ended at the same 2 points as I did in experiment 1. But in experiment 2, I followed a very different path in the PV diagram. Right? Now here's a key thing. Since experiment 2 started and stopped at the same 2 points as experiment 1, experiment 2 has the same value for delta U as experiment 1. Delta U, or U, being a function of state, only depends upon your stopping point and your starting point, and doesn't depend on what you did in between. So these 2 different experiments have the same value for delta U. Okay? I contend that they do not have the same amount of work. As we will learn later on, and as you might remember from Physics 111, although it was a while ago, a representation of the work done on a system in a PV diagram is it is the negative of the area under the curve. It's a nice graphical interpretation of work in a PV diagram. The work done on a system is the negative of the area under the PV curve. Well, just look at these two, the PV curves for these 2 experiments. The blue one is for experiment 1, and the 2 red lines are for experiment 2. It's pretty clear from that there's different amounts of area under those 2 curves, yes? So I know right away that the work done in the 2 experiments is different. Different amounts of work are done. Okay? Yet the delta U is the same. But the first law of thermodynamics says that delta U equals Q plus W. So if delta U is the same for both experiments, but W is different for the 2 experiments, then Q must be different for the 2 experiments, but Q plus W is the same. Okay? So both Q and W separately, they're different for different experiments. But Q plus W equals delta U, that's the same for those 2 experiments. Okay? So it's very important to remember, delta U does not depend upon how you go from point 1 to point 2. But Q and W separately do depend on how you go from point 1 to point 2 in a PV diagram. Yes?
Question on the apparatus. If the pressure balances, it's a question on the locking pin. If we don't have the locking pin in, it's just the pressure pushing up to hold it constant. Wouldn't the locking pin having that in and the pressure not having to hold that up, wouldn't it cause like a jump between the pressure?
You mean the pressure of the gas? Here, the pressure of whatever's on top and the pressure of the gas?
Yeah.
They won't necessarily be equal if the locking pin is there, because the locking pin is providing another force.
Yeah.
Yes,
Okay.
that's right. That's right. Okay, lastly, just a little bit of notation. Something you want to get used to or be aware of. Especially if you're going on to higher level study and you take a grad level course in statistical mechanics or thermodynamics. Let's write down the first law of thermodynamics for the specialized case of infinitesimal energy transfers. Physicists love infinitesimals because they are conceptually simple. Okay? So how do we write down the first law? What's the notation we use when we're just considering infinitesimal energy transfers between the system and its surroundings? First of all, we change delta U to du. You're used to the d notation for infinitesimals. Okay? So delta U, a finite amount of internal energy change, becomes an infinitesimal amount of internal energy change. And that's what the du means. It means a tiny change in the internal energy of the system. Okay? All right, here's the thing you don't want to do. You don't change Q to dQ. And you don't change W to dW. Because to a mathematician, I'm not quite exactly sure to a physicist, I'm not quite exactly sure what a mathematician would say. To a physicist, to write, say, dQ, is to conceptually say that it is a tiny change in Q. Now that's bordering on bad language, because that's like saying, well, there was a certain amount of Q to begin with, and a certain amount of Q to end, and it changed. In other words, it's starting to sound like you're saying the thing has a certain amount of heat, and you're just changing it by a little bit. That's not what we're talking about. Okay? You can have a tiny amount of energy come in or out as heat, come in or go out. But that's not what we mean by dQ. So what you'll see in some books is they'll write dQ and they'll put a bar through the D. And they'll call it an inexact differential. It just means a tiny energy transfer. Okay? Just don't call it a tiny change in heat. It's a tiny energy transfer as heat. Similar with W. Don't call it dW. Or don't write dW, write dW bar. Okay? It's a tiny energy transfer as work. It's not a change in work. Okay? But this is a change in energy. That's the way a lot of the advanced books will write it. If they're writing the first law, and there it is, in infinitesimal notation. Your author doesn't like the bar symbol through the T's. So he just goes his own way. I'm not sure what I think about it, but I'll just tell you what your text does. He has the infinitesimal form for du, that's a tiny change in energy, and he just uses Q and W, even though they mean infinitesimal amounts. And he says, you'll have to figure it out from my context of my sentence that I'm talking about an infinitesimal energy transfer, Q and W. Just warning you about that. Okay. So, that was a pretty substantive set of slides. Remember, it's all on Blackboard. Okay? First law of thermodynamics. We're going to be applying that. But now what I want to do is talk for a while. Let me get some light on the board. Now I'm going to transition to the board for a while. And I'm going to talk some more. I'm going to talk about something we do also talk about in intro physics, but I'm going to spend some considerable time talking about it. One of our favorite systems to study when we study thermodynamics and physics is what's called the ideal gas. Okay, so I want to talk about that in some detail. So now we're up to section 3. And so right now I'm going to describe this as an empirical model of a dilute gas. This result is called, by most people, at least in physics, the ideal gas, quote-unquote, law. I put the word law in quotes because we tend to use the word law in physics. We reserve that word law for things that are fundamental ideas, like conservation of energy, or conservation of momentum, or something like that. This is just a useful experimental result. Okay? And that's what empirical means. Remember, empirical means deduced by experiment. let's be a little more clear what we mean by dilute. Okay, so what do we mean when we say a gas is dilute? Okay, well, that's another way of saying it has a low density, which means that the average space between molecules is much larger than the molecules themselves. Okay? That's what we're going to mean by dilute. The average space between two molecules is much larger than the molecules themselves. Now, how do we determine how big a molecule is, in some sense? Well, to a theorist, anyways, what you do is you go to quantum mechanics, the molecule after all, you use whatever techniques you know of to calculate its wave function. You then figure out the spatial extent of the wave function. How much does it extend spatially from side to side of the molecule? That's the size. Okay? We're going to be in a limit where the two molecules are so far apart that their wave functions in essence don't really overlap each other. Okay, so what is this empirical result? Meaning deduced by experiment. So I'll write it as experimental. And if you take, say, chemistry, they talk about Boyle's law and Charles' law, because there are people who did these experiments back in the day to figure out how a low density, a dilute gas behaves. Okay? But it's really just one result. Okay? And as you probably remember, this model for describing the behavior of a dilute gas depends on several key properties. You know, the symbol P is the pressure of the gas. Okay? So let's make sure we are all on the same wavelength, so to speak, with regard to the symbols. This is the pressure of the gas that it exerts on the walls of the container. That's the force per unit area that it exerts on the walls of the container. We're going to do everything here in SI units. The SI unit is the Pascal. Okay? That is denoted by the symbol capital P little a. That's the unit. That's the symbol for Pascal. Okay? Atmospheric pressure, at least what's called standard temperature and pressure, is 1.01 times 10 to the 5th pascals, i.e. 101,000 pascals is what we call atmospheric pressure. That's at least something close to that is what you're used to being in just by standing here in Earth's atmosphere. Okay? From the weight of all the air on top of you. If you want to have a sense of how much pressure 1 pascal is, it is, take just a dollar bill, flatten it out on a tabletop, it's the weight of a dollar bill spread out over the area of the dollar bill. That's 1 pascal, roughly 1 pascal. Okay? Any bill. Any US bill. Okay? All right, we also, of course, need the volume of the gas, pressure times volume. So this is the volume in meters cubed. This is SI. The SI unit of volume is meter cubed. Okay. Then we have over here a quantity that is somehow measuring how much gas there is. There's more than one way to do that. One way, symbol little n, is to tell how many moles of the gas there are. Number of moles of the gas. Mole is an SI unit for basically amount of material. The symbol is for the unit is MOL. The unit mole is denoted MOL. Okay? Then there's just a constant to get all the units on the two sides to come out the same. Okay? Symbol is R. We'll just call it the gas constant. Some books will call it the universal gas constant, which makes it sound really important. But all they mean by universal in the universal gas constant is that it's the same constant no matter what kind of gas you're studying, as long as it's dilute. Okay? Its value in SI is 8.31. The units must be, in order for the two sides to end up having the same units, joule per mole times Kelvin. And then lastly on the right-hand side is the temperature, and it's got to be in Kelvin. So it's the absolute temperature in Kelvin. Not degrees Kelvin, remember, just Kelvin. It can't be in degrees Celsius, because you could end up having a negative value here, yes? For example. But at least for a dilute gas in a box, you're not going to have a negative pressure. Absolute pressure. P is over there. Okay. Remember this from intro physics and or chemistry? Okay? Pressure times volume equals number of moles times the gas constant times the temperature. And you can do all kinds of homework problems and experiments where you fix one of these things and you then look at the other two and how they vary relative to each other. Okay? All right, let me show you another way to write this experimental result. Okay? Completely equivalent, just slightly different bookkeeping. Okay? I'm going to, on the right-hand side, I'm going to multiply and divide on the right-hand side by some constant. Okay? And that constant is called Avogadro's number, which is the number of particles in a mole. So I'm going to take number of moles, and I'm going to multiply, here's my symbol for Avogadro's number, N sub A, capital N sub A, Avogadro's number, which you might remember is 6.02 times 10 to the 23, and the unit of Avogadro's number is inverse mole, because it's 6.02 times 10 to the 23 particles per mole. Okay? So I'm multiplying by Avogadro's number, and I have to divide too, so I don't change the result by Avogadro's number. Times T. So I haven't technically changed the result. Okay? Just multiplied and divided by the number of particles in a mole. Now I want to reinterpret, let me do this over here, what these think quantities are. Any thoughts on what that product is? Little n, remember, is the number of moles of gas. And I multiplied that by Avogadro's number. What is that going to give me? Number of molecules or atoms, right? The number of moles times the number of particles per mole is just the total number of particles in the gas. Okay? The symbol that everybody uses for that is just a capital N with no other notation. Watch out, I got lots of N's here. Okay? This capital N is the total number of, I'm going to use the word molecules. Okay? Capital N is the total number of molecules that the gas contains. Right? So this is going to be replaced, this product, with just the total number of molecules. The thing in parentheses is one constant divided by another constant. I could just leave that completely as it is because it's just a constant. But everybody gives that a new name. Okay? So we might as well do that. So we're going to define a new constant. For now, it's just going to be what you get when you take the gas constant divided by Avogadro's number. We will call it, and we will use the symbol I do anyways, little k sub b, and it is called Boltzmann's constant, after Ludwig Boltzmann. in some sense, the father of statistical mechanics. He was. Okay? Warning, your book uses just the symbol K for Boltzmann's constant. But we use K a lot in physics, so I like to add the B when I mean Boltzmann's constant. Okay? What is the value of Boltzmann's constant? Well, it's not too hard to figure out. You see how you would do it, right? Just put in 8.31 joule per mole Kelvin for the gas constant, 6.02 times 10 to the 23 per mole for Avogadro's number. See what your calculator gives you, yes? To 3 sig figs, it's 1.38 times 10 to the negative 23. Let's think about what the units would be. Joule per mole Kelvin per mole. So what am I left with? Joules per Kelvin. So the unit of this Boltzmann constant is the unit of energy divided by the unit of temperature. Okay? With that new definition, let's write the ideal gas law in the second way. Pressure times volume is total number of particles times Boltzmann's constant times temperature. Okay? So this is the alternative, ideal gas law, alternative. Okay? Don't get the two versions confused. Don't swap symbols. You can't use a little n with K sub B. You can't use a big N with R. Just watch out for that. I'll just also then briefly mention that this way of introducing Boltzmann's constant doesn't do it justice, because it makes it seem like it's just an afterthought of one constant divided by another. It is in fact a much more fundamental constant of nature than R is, as you learn when you study more physics, because it shows up in more fundamental physics results than R does. R only shows up in one physics result. Okay? So this is actually a much more important constant of nature than R is. Also, I would say more important than Avogadro's number, but that might be something debatable. Okay, one more thing I'll do today, and then we'll stop. Let's use the ideal gas law to estimate the average molecular separation in an ideal gas at room temperature, in atmospheric pressure. Okay? So let's use the ideal gas law to estimate the average molecular separation if the pressure is atmospheric pressure and the temperature of the gas is room temperature. Let's take that to be 280 Kelvin. Remember I said 300 Kelvin is a warm room, so we'll say 280 Kelvin. By the way, all dilute gases follow this. Doesn't matter whether it's nitrogen or oxygen or a combination of nitrogen and oxygen, right? They all follow this. So it doesn't matter what kind of gas I'm talking about. All right, so what I'm going to do is first find the volume per molecule. How much volume is there for each molecule in a particular box? Okay? I'm going to use this form of the ideal gas law. There's the total volume of the box that contains the gas. There's the total number of molecules of gas that there are in the box. So I think that the volume per molecule is the total volume divided by the total number of molecules. That will give me how much volume is available for each molecule. The ideal gas law tells me that the volume per molecule, just rearrange it and solve for V over M, is the pressure, is kT over the pressure. Okay? So I just plug in the temperature I assumed and the pressure I assumed. Let's see what we get. Okay? Before I do that, let me just make sure it's clear. Let's say we've got the gas inside some box. Okay? There's a box of gas. It's got a volume V. I'm finding the volume in here that each molecule has. So I'm just imagining that I can divide it up into little sub-volumes, like this cube down here. And then each one of those contains one molecule. Now, that's much bigger than really, okay? But right? There's a volume per molecule, V over N. Then there's you can imagine filling the box with those little sub-boxes. One molecule per sub-box. And let's say the molecule's dimensions, the box's dimensions, are little l, the sub-box. Then what my point is, that little l is the distance between the atom in that box and the atom in the neighboring box. I.e. the L is what I'm looking for. It's the average molecular separation. It's an estimate of it. Okay? So L, which is just one side of this little sub-box, so that's got to be the volume of that sub-box to the 1/3 power. Because the sub-box's volume is L cubed. And that distance L is the average molecular separation. It's an estimate of it anyways, assuming it's a dilute gas and obeys the ideal gas law. So that's going to be Boltzmann's constant times the temperature over the pressure to the 1/3 power. Let's see what number we get for this separation. So Boltzmann's constant, 1.38 times 10 to the negative 23 joule per Kelvin. We took the temperature to be room temperature. We took that to be 280 Kelvin. We took the gas to be atmospheric pressure, 1.01 times 10 to the 5th Pascal. This you can check for yourself, and you probably should. All of this to the 1/3 power will have units of meters. And the number will be 3.37 times 10 to the minus 9. So the way the physicist would write this is 3.37 nanometers. Well, I expected the average separation between two molecules to be pretty small. They are molecules. If I got something like a meter, that wouldn't make any sense. That would mean if this were, say, gas, were air in a room, and there was on average a meter between molecules, I could very easily find myself standing in a place where there's no molecule to breathe. Doesn't make any sense at all, right? It's got to be small. It's 3.37 meters. You compare that with the average size of a molecule, say, of air. Okay? I'll call that D. That's approximate size of an N2 molecule. That's the most prevalent molecule in the air in a room. Nitrogen, N2. That turns out to be about 0.3 nanometers. So the ratio of the distance between two molecules to the size of a molecule is a little bit more than 10. It's about 11. Okay. That's enough, at least it's a factor of 10, to say we're in the low density or dilute limit, because the distance between two molecules is pretty big compared to the size of the molecules. Okay? So we will treat room temperature and atmospheric pressure gas in a box, i.e., say, for example, the air in this room, to be an ideal gas. We'll learn later on in the semester, we'll look at some gases that cannot be treated as an ideal gas. And there's some pretty important counterexamples. All right, that's a good stop. I'll see you on Tuesday. Well, some of you I'll see before that.